Tensors are geometric objects that describe linear relations between vectors, scalars, and other tensors. Elementary examples of such relations include the dot product, the cross product, and linear maps. Vectors and scalars themselves are also tensors. A tensor can be represented as a multidimensional array of numerical values. The order of a tensor is the dimensionality of the array needed to represent it, or equivalently, the number of indices needed to label a component of that array. For example, a linear map can be represented by a matrix and therefore as a second-order tensor. A vector can be represented as a one-dimensional array and is a first-order tensor. Scalars are single numbers and are thus zeroth-order tensors. It is very important not to confuse dimensions of the array with dimensions of the underlying vector space. Tensors are used to represent correspondences between sets of geometric vectors. For applications in engineering and Newtonian physics, these are normally Euclidean vectors. For example, the Cauchy stress tensor T takes a direction v as input and produces the stress T, v, on the surface normal to this vector for output, thus expressing a relationship between these two vectors, shown in the figure. Because they express a relationship between vectors, tensors themselves must be independent of a particular choice of coordinate system. Finding the representation of a tensor in terms of a coordinate basis results in an organized multidimensional array representing the tensor in that basis or frame of reference. The coordinate independence of a tensor then takes the form of a covariant transformation law that relates the array computed in one coordinate system to that computed in another one. The precise form of the transformation law determines the type of the tensor. The tensor type is a pair of natural numbers where n is the number of contravariant indices and m is the number of covariant indices. The total order of a tensor is the sum of these two numbers. Tensors are important in physics because they provide a concise mathematical framework for formulating and solving physics problems in areas such as elasticity, fluid mechanics, and general relativity. Tensors were first conceived by Tullio Levi-Civita and Gregorio Ricci Calculus, who continued the earlier work of Bernhard Riemann and Erwin Bruno Christoffel and others, as part of the absolute differential calculus. The concept enabled an alternative formulation of the intrinsic differential geometry of a manifold in the form of the Riemann curvature tensor. Definition: there are several approaches to defining tensors. Although seemingly different, the approaches just describe the same geometric concept using different languages and at different levels of abstraction. As multidimensional arrays, just as a vector with respect to a given basis is represented by an array of one dimension, any tensor with respect to a basis is represented by a multidimensional array. The numbers in the array are known as the scalar components of the tensor or simply its components. They are denoted by indices giving their position in the array, as subscripts and superscripts, after the symbolic name of the tensor. In most cases, the indices of a tensor are either covariant or contravariant, designated by subscript or superscript, respectively. The total number of indices required to uniquely select each component is equal to the dimension of the array, and is called the order, degree or rank of the tensor. For example, the entries of an order 2 tensor T would be denoted Tij, Tj, Tij, or Tij, where I and j are indices running from 1 to the dimension of the related vector space. When the basis and its dual coincide, the distinction between contravariant and covariant indices may be ignored. In these cases Tij or Tij could be used interchangeably. Just as the components of a vector change when we change the basis of the vector space, the entries of a tensor also change under such a transformation. Each tensor comes equipped with a transformation law that details how the components of the tensor respond to a change of basis. The components of a vector can respond in two distinct ways to a change of basis, where the new basis vectors are expressed in terms of the old basis vectors as where Ej is a matrix, and in the second expression the summation sign was suppressed. The components, vi, of a regular vector, v, transform with the inverse of the matrix R, where the hat denotes the components in the new basis, while the components, v, of a covector, w transform with the matrix R itself. The components of a tensor transform in a similar manner with a transformation matrix for each index. If an index transforms like a vector with the inverse of the basis transformation, it is called contravariant and is traditionally denoted with an upper index, while an index that transforms with the basis transformation itself is called covariant and is denoted with a lower index. The transformation law for an order M tensor with n contravariant indices and MAN covariant indices is thus given as: such a tensor is said to be of order or type. This discussion motivates the following formal definition. Definition: a tensor of type is an assignment of a multidimensional array to each basis f equals such that, if we apply the change of basis, then the multidimensional array obeys the transformation law. The definition of a tensor as a multidimensional array satisfying a transformation law traces back to the work of Ricci. Nowadays, this definition is still used in some physics and engineering textbooks. Tensor fields. In many applications, especially in differential geometry and physics, it is natural to consider a tensor with components that are functions of the point in a space. This was the setting of Ricci's original work. In modern mathematical terminology, such an object is called a tensor field, often referred to simply as a tensor. In this context, a coordinate basis is often chosen for the tangent vector space. The transformation law may then be expressed in terms of partial derivatives of the coordinate functions, defining a coordinate transformation. As multilinear maps, a downside to the definition of a tensor using the multidimensional array approach is that it is not apparent from the definition that the defined object is indeed basis independent, as is expected from an intrinsically geometric object. Although it is possible to show that transformation laws indeed ensure independence from the basis, sometimes a more intrinsic definition is preferred. One approach is to define a tensor as a multilinear map. In that approach, a type tensor T is defined as a map where V is a vector space and V is the corresponding dual space of covectors, which is linear in each of its arguments. By applying a multilinear map T of type to a basis edge for V and a canonical cobasis I micron I for V, an dimensional array of components can be obtained. A different choice of basis will yield different components. But, because T is linear in all of its arguments, the components satisfy the tensor transformation law used in the multilinear array definition. The multidimensional array of components of T thus form a tensor according to that definition. Moreover, such an array can be realized as the components of some multilinear map T. This motivates viewing multilinear maps as the intrinsic objects underlying tensors. Using tensor products. For some mathematical applications, a more abstract approach is sometimes useful. This can be achieved by defining tensors in terms of elements of tensor products of vector spaces, which in turn are defined through a universal property. A type tensor is defined in this context as an element of the tensor product of vector spaces. If phi is a basis of V and Wj is a basis of W, then the tensor product has a natural basis. The components of a tensor T are the coefficients of the tensor with respect to the basis obtained from a basis I for V and its dual I micron J, that is. Using the properties of the tensor product, it can be shown that these components satisfy the transformation law for a type tensor. Moreover, the universal property of the tensor product gives a one-to-one correspondence between tensors defined in this way and tensors defined as multilinear maps. Examples. This table shows important examples of tensors, including both tensors on vector spaces and tensor fields on manifolds. The tensors are classified according to their type, where n is the number of contravariant indices, m is the number of covariant indices, and n plus m gives the total order of the tensor. For example, a bilinear form is the same thing as a tensor. An inner product is an example of a tensor, but not all tensors are inner products. In the entry of the table, M denotes the dimensionality of the underlying vector space or manifold because for each dimension of the space, a separate index is needed to select that dimension to get a maximally covariant antisymmetric tensor. Raising an index on an tensor produces an tensor. This can be visualized as moving diagonally up and to the right on the table. Symmetrically, Lowering an index can be visualized as moving diagonally down and to the left on the table. Contraction of an upper with a lower index of an tensor produces an tensor. This can be visualized as moving diagonally up and to the left on the table. Notation: Ricci Calculus. Ricci Calculus is the modern formalism and notation for tensor indices, indicating inner and outer products, covariants and contravariants, summations of tensor components, symmetry and antisymmetry, and partial and covariant derivatives. Einstein summation convention. The Einstein summation convention dispenses with writing summation signs, leaving the summation implicit. Any repeated index symbol is summed over. If the index I is used twice in a given term of a tensor expression, it means that the term is to be summed for all I. Several distinct pairs of indices may be summed this way. Penrose graphical notation. Penrose graphical notation is a diagrammatic notation which replaces the symbols for tensors with shapes, and their indices by lines and curves. It is independent of basis elements, and requires no symbols for the indices. Abstract index notation. The abstract index notation is a way to write tensors such that the indices are no longer thought of as numerical, but rather are indeterminates. This notation captures the expressiveness of indices and the basis independence of index-free notation. Component-free notation. A component-free treatment of tensors uses notation that emphasizes that tensors do not rely on any basis, and is defined in terms of the tensor product of vector spaces. Operations. There are a number of basic operations that may be conducted on tensors that again produce a tensor. The linear nature of tensor implies that two tensors of the same type may be added together, and that tensors may be multiplied by a scalar with results analogous to the scaling of a vector. On components, these operations are simply performed component for component. These operations do not change the type of the tensor, however there also exist operations that change the type of the tensors. Tensor product. The tensor product takes two tensors, S and T, and produces a new tensor, S'(T), whose order is the sum of the orders of the original tensors. When described as multilinear maps, the tensor product simply multiplies the two tensors, that is, which again produces a map that is linear in all its arguments. On components the effect similarly is to multiply the components of the two input tensors, that is, if S is of type and T is of type, then the tensor product S'(T) has type. Contraction. Tensor contraction is an operation that reduces the total order of a tensor by 2. More precisely, it reduces a type tensor to a type tensor. In terms of components, the operation is achieved by summing over one contravariant and one covariant index of tensor. For example, a tensor can be contracted to a scalar through where the summation is again implied. When the tensor is interpreted as a linear map, this operation is known as the trace. The contraction is often used in conjunction with the tensor product to contract an index from each tensor. The contraction can also be understood in terms of the definition of a tensor as an element of a tensor product of copies of the space V with the space V by first decomposing the tensor into a linear combination of simple tensors, and then applying a factor from V to a factor from V. For example, a tensor can be written as a linear combination. The contraction of T on the first and last slots is then the vector raising or lowering an index. When a vector space is equipped with a non-degenerate bilinear form, operations can be defined that convert a contravariant index into a covariant index and vice versa. A metric tensor is a tensor. It is thus possible to contract an upper index of a tensor with one of lower indices of the metric tensor in the product. This produces a new tensor with the same index structure as the previous, but with lower index in the position of the contracted upper index. This operation is quite graphically known as lowering an index. Conversely, the inverse operation can be defined, and is called raising an index. This is equivalent to a similar contraction on the product with a tensor. This inverse metric tensor has components that are the matrix inverse of those of the metric tensor. Applications: Continuum Mechanics. Important examples are provided by Continuum Mechanics. The stresses inside a solid body or fluid are described by a tensor. The stress tensor and strain tensor are both second-order tensors, and are related in a general linear elastic material by a fourth-order elasticity tensor. In detail, the tensor quantifying stress in a three-dimensional solid object has components that can be conveniently represented as a 3A, A 3 The three faces of a cube-shaped infinitesimal volume segment of the solid are each subject to some given force. The force's vector components are also 3 in number. Thus, 3A, A 3, or 9 components are required to describe the stress at this cube-shaped infinitesimal segment. Within the bounds of this solid is a whole mass of varying stress quantities, each requiring 9 quantities to describe. Thus, a second-order tensor is needed. If a particular surface element inside the material is singled out, the material on one side of the surface will apply a force on the other side. In general, this force will not be orthogonal to the surface, but it will depend on the orientation of the surface in a linear manner. This is described by a tensor of type, in linear elasticity, or more precisely by a tensor field of type, since the stresses may vary from point to point. Other examples from physics, common applications include electromagnetic tensor in electromagnetism, finite deformation tensors for describing deformations and strain tensor for straining continuum mechanics, permittivity and electric susceptibility are tensors in anisotropic media, four tensors in general relativity, used to represent momentum fluxes, spherical tensor operators are the eigenfunctions of the quantum angular momentum operator in spherical coordinates, diffusion tensors, the basis of diffusion tensor imaging, represent rates of diffusion in biologic environments. Quantum mechanics and quantum computing utilize tensor products for combination of quantum states. Applications of tensors of order greater than 2, the concept of a tensor of order 2 is often conflated with that of a matrix. Tensors of higher order do however capture ideas important in science and engineering, as has been shown successively in numerous areas as they develop. This happens, for instance, in the field of computer vision, with the trifocal tensor generalizing the fundamental matrix. The field of nonlinear optics studies the changes to material polarization density under extreme electric fields. The polarization waves generated are related to the generating electric fields through the nonlinear susceptibility tensor. If the polarization P is not linearly proportional to the electric field E, the medium is termed nonlinear. To a good approximation, P is given by a Taylor series in E whose coefficients are the nonlinear susceptibilities. Here is the linear susceptibility, gives the Pockels effect and second harmonic generation, and gives the Kerr effect. This expansion shows the way higher-order tensors arise naturally in the subject matter. Generalizations, tensors in infinite dimensions. The notion of a tensor can be generalized in a variety of ways to infinite dimensions. One, for instance, is via the tensor product of Hilbert spaces. Another way of generalizing the idea of tensor, common in nonlinear analysis, is via the multilinear maps definition where instead of using finite-dimensional vector spaces and their algebraic duals, one uses infinite-dimensional Banach spaces and their continuous dual. Tensors thus live naturally on Banach manifolds. Tensor densities. The concept of a tensor field can be generalized by considering objects that transform differently. An object that transforms is an ordinary tensor field under coordinate transformations, except that it is also multiplied by the determinant of the Jacobian of the inverse coordinate transformation to the power, is called a tensor density with weight. Invariantly, in the language of multilinear algebra, one can think of tensor densities as multilinear maps taking their values in a density bundle such as the space of n forms, as opposed to taking their values in just a higher weights then just correspond to taking additional tensor products with this space in the range. A special case are the scalar densities. Scalar 1 densities are especially important because it makes sense to define their integral over a manifold. They appear, for instance, in the Einstein-Hilbert action in general relativity. The most common example of a scalar 1 density is the volume element, which in the presence of a metric tensor G is the square root of his determinant in coordinates, denoted. The metric tensor is a covariant tensor of order 2, and so its determinant scales by the square of the coordinate transition, which is the transformation law for a scalar density of weight plus 2. More generally, any tensor density is the product of an ordinary tensor with a scalar density of the appropriate weight. In the language of vector bundles, the determinant bundle of the tangent bundle is a line bundle that can be used to twist other bundles W times. While locally the more general transformation law can indeed be used to recognize these tensors, there is a global question that arises, reflecting that in the transformation law one may write either the Jacobian determinant, or its absolute value. Non-integral powers of the transition functions of the bundle of densities make sense, so that the weight of a density, in that sense, is not restricted to integer values. Restricting to changes of coordinates with positive Jacobian determinant is possible on orientable manifolds, because there is a consistent global way to eliminate the minus signs. But otherwise the line bundle of densities and the line bundle of n-forms are distinct. For more on the intrinsic meaning, see density on a manifold. Spinors. When changing from one orthonormal basis to another by a rotation, the components of a tensor transform by that same rotation. This transformation does not depend on the path taken through the space of frames. However, the space of frames is not simply connected, there are continuous paths in the space of frames with the same beginning and ending configurations that are not deformable one into the other. It is possible to attach an additional discrete invariant to each frame called the spin that incorporates this path dependence, and which turns out to have values of a plus or minus 1. A spinor is an object that transforms like a tensor under rotations in the frame, apart from a possible sign that is determined by the spin. History. The concepts of later tensor analysis arose from the work of Carl Friedrich Gauss in differential geometry, and the formulation was much influenced by the theory of algebraic forms and invariants developed during the middle of the 19th century. The word tensor itself was introduced in 1846 by William Rowan Hamilton to describe something different from what is now meant by a tensor. The contemporary usage was introduced by Woldemar Voigt in 1898. Tensor calculus was developed around 1890 by Gregorio Ricci Calculus under the title Absolute Differential Calculus, and originally presented by Ricci in 1892. It was made accessible to many mathematicians by the publication of Ricci and Tullio Levi Civita's 1900 classic text Mar copyright Thodes de Calcul differ copyright Rential Absolute les applications. In the 20th century, the subject came to be known as tensor analysis, and achieved broader acceptance with the introduction of Einstein's theory of general relativity, around 1915. General relativity is formulated completely in the language of tensors. Einstein had learned about them, with great difficulty, from the geometer Marcel Grossmann. Levi Civita then initiated a correspondence with Einstein to correct mistakes Einstein had made in his use of tensor analysis. The correspondence lasted 1915–17, and was characterized by mutual respect. I admire the elegance of your method of computation. It must be nice to ride through these fields upon the horse of true mathematics while the like of us have to make our way laboriously on foot. Tensors were also found to be useful in other fields such as continuum mechanics. Some well-known examples of tensors in differential geometry are quadratic forms such as metric tensors, and the Riemann curvature tensor. The exterior algebra of Hermann Grassmann, from the middle of the 19th century, is itself a tensor theory, and highly geometric, but it was some time before it was seen, with the theory of differential forms, as naturally unified with tensor calculus. The work of Apermel Lie cut and made differential forms one of the basic kinds of tensors used in mathematics. From about the 1920s onwards, it was realized that tensors play a basic role in algebraic topology. Correspondingly, there are types of tensors at work in many branches of abstract algebra, particularly in homological algebra and representation theory. Multilinear algebra can be developed in greater generality than for scalars coming from a field. For example, scalars can come from a ring. But the theory is then less geometric and computations more technical and less algorithmic. Tensors are generalized within category theory by means of the concept of monoidal category, from the 1960s. See also, Foundational, Cartesian tensor, fiber bundle, Glossary of tensor theory, multilinear projection, one form, tensor product of modules, applications, application of tensor theory in engineering, covariant derivative, curvature, diffusion tensor MRI, Einstein field equations, fluid mechanics, multilinear subspace learning, Riemannian geometry, structure tensor, tensor decomposition, tensor derivative, tensor software, notes. References, general. Specific. This article incorporates material from Tensor on Planet Math, which is licensed under the Creative Commons Attribution Share Alike license. External links, Weierstein, Eric W., Tensor, Math World. Introduction to Vectors and Tensors, Vol 1, Linear and Multilinear Algebra by Ray M. Bowen and C. C. Wang. Introduction to Vectors and Tensors, Vol 2, Vector and Tensor Analysis by Ray M. Bowen and C. C. Wang. An Introduction to Tensors for Students of Physics and Engineering by Joseph C. Kolecki, released by NASA, a discussion of the various approaches to teaching tensors, and recommendations of textbooks, Introduction to Tensors, an original approach by S. Poirier, a quick introduction to tensor analysis by R. A. Sharapov.